All right. How's it going, guys? Hope you guys are hanging in there with this chapter 10. I know circles is a little hard, lots of formulas and relationships, and section 5 just adds a whole lot more. So you probably will be relying on your notes a little bit more than usual for this section. So let's just jump right into it. We're going to be talking about angles relating to arcs on a circle. And the formula is really going to be based on where you find the vertex of your angle. So we're going to break this up into different categories of angles and where their vertices are. So we're going to start off with angles whose vertices are actually on the circle. And one of these we've already done. We did it in the last section, and that's the inscribed angle. So we're talking about angle B right here as the inscribed angle, and that it relates to the intercepted arc. In the formula, that angle B is half of the arc. And we talked about that in the last section, so that should be pretty good. I'm not going to spend time on that. But the next one is a new one. It's called the tangent chord angle. So it's an angle that's made with a tangent line and a chord somewhere in the circle. And this point of tangency is the vertex of the angle that we're talking about. And so if you notice, there's actually two angles. There's an angle on the left side, or I'm sorry, that's the right side, and the left side. So let's talk about, first of all, this acute angle, this little one right here. The formula that you would use to figure out angle ACB is related to the red arc. It's the little arc that is cut off by the chord. Okay, so the relationship is that this angle is half of this arc. And that might seem very similar to this relationship, that this inscribed angle is half of that arc. And you're not wrong. They are the same relationship because the vertex of the angle is found in the same place on the circle. So you might be asking yourself, well, what about this angle over here? Well, this is also a tangent chord angle, but it's just dealing with the bigger arc, right? The major arc. So it has the same relationship. It's half of this big arc. So you just have to pay attention to which angle you're looking at and do half of the correct corresponding arc. All right, so give this a shot. If I give you this arc, AB is 130, what is the measure of angle 1? And I'm hoping you just took half of that and said it was 65 degrees. Next question, we have this tangent and this chord, and the tangent chord angle is 125. So what is the measure of arc KJL? I'm hoping all you did was double the 125 and you get the 250 degrees. All right, next relationship. Now we're going to talk about angles whose vertices are inside the circle. And one of those we've already done before, right? We did the central angle. We started off this chapter pretty much dealing with that special central angle and how it's equal to the arc that it cuts off, that intercepted arc. Okay, so I'm not going to spend time on that. What else we could do is, what if the vertex of our angle is inside the circle, but it's not the center of the circle? Which means you have these two chords, or they could be two secants, right? We call this the chord angle because we really are just looking at these specific chords that we have and how they create these like vertical angles, right? And if you look at these like angle 1 and angle whatever this angle is, I don't know, I didn't number it, how those are two vertical angles, they're congruent to each other, but they each have these kind of arcs that are associated with those two angles. So when you go to figure out what the measure of one of these vertical angles is, you actually are taking the average of the red and the blue arc. So you add them together, add those two arcs together, and then divide it by 2. Okay, we could do the same thing for angle 2, only you're going to use arc AB an arc CD instead. So you really just have to pay attention to what angle of these 4 angles that you're looking for and figure out the 2 correct arcs that are kind of opposite those vertical angle pairs. Of course, if you already had angle 1, you could just find the supplement to get angle 2, but I'm just trying to show that you just have to pick out the right arcs. Okay? So those are what you're going to do if angles have vertices inside the circle. So here's an example. I want to figure out this angle. I didn't give this a letter, but it's this angle that we're looking for. So this angle is vertical to this one, and so we're dealing with these 2 arcs, 130 and 156. So I'm going to take the average of those 2 arcs, and when I do, I get 143 degrees. So that's how you would do that. All right, so now that leaves us with angles whose vertices are outside of the circle. There's 3 of these. Okay, so the first one is called the secant-secant angle. So if you have this secant and this secant and they intersect at point B, it creates this little angle that's outside of the circle. Well, these 2 secants, when they cut through the circle, they create these 2 intersected arcs, right? So we have the blue arc and the red arc. Well, the way that we figure out the measure of angle A, or I'm sorry, the measure of angle B, is not the average. We're not going to add the 2 arcs and divide by 2. Instead, we're going to subtract the 2 arcs and divide by 2. Always make sure you're taking the big arc minus the little arc. We do not want to get a negative angle, okay? So negative angles you get to deal with next year, but this year, no negative angles. So always take the big arc minus the little arc and then divide by 2. This is the same relationship for any angle whose vertex is outside of the circle. So when we're talking about a secant tangent, we still have these 2 arcs, the red arc and the blue arc. It just happens that they have a point in common, this point of tangency. But the formula is still the same. Take the big arc and subtract the little arc, and then divide it by 2. Okay, and then the last one that we could have is, oh, I guess we're going to do an example before that. Ha! New for me. Okay, so let's take a look at this example. I need to figure out what x is. They give me this is 76 degrees, and this big arc right here is 178 degrees. So why don't you try to figure out what x would be? I'll give you a second to do that. Okay, so hopefully you just took this arc, subtracted that arc, and divided by 2, and you got 51 degrees. Let's try the other example. So the other example is this. We've got this angle this time is 30, and they give us this arc is 44, and we are looking for arc AC. So this time what I would like you to answer for me is, what do you think the equation would be that we would set up to solve for x? And this kind of uses our formula. It's the same formula that this angle is half of this arc minus that arc. So when we plug that into our formula, this time we know what the angle is, and we're solving for the big arc. So I hope this is what you wrote down. And now we have to solve that. So you could distribute the 1/2 if you like to do that. Algebraically, I think it's easier to just multiply both sides by 2 and get rid of that fraction. So when I do that, I get 60 equals x minus 44. And then I can just add the 44 and I get 104. Okay, now we're ready to talk about the last angle that's outside of the circle, which is the tangent-tangent angle. Now the tangent-tangent angle has the 2 arcs, once again, the big red arc and the little blue arc, but both of those arcs share these points of tangency. So you kind of have to be careful when you're looking at it to read off the correct angle measures, or I'm sorry, arc measures. So angle B is the same relationship, half of the big arc minus the little arc. However, I want you to consider this. Take a look at this circle with the tangent angle, and if I called this arc, the blue arc, X, because the circle is 360 degrees, that means that the remaining red arc is 360 minus whatever that arc is, right? So if I plug these two arc measures into this formula, take a look at what happens. It's pretty cool. So we do half of the big arc minus the little arc, simplify, combine like terms, and distribute the 1/2. And what it shows us is this relationship between the tangent angle and this minor arc. And it looks like they're supplementary. And in fact, that is the next theorem that we talk about, is that the measure of a tangent angle is supplementary to the central angle that intercepts that minor arc, or just supplementary to that minor arc. So either one of these is fine as long as you understand this angle and that angle, or this angle and that arc add to 180 degrees. So your last question for this video is, if I tell you that this arc is 130 degrees, what is the measure of angle B? I'm hoping that you just said it's 50 degrees. But I want you to think of this. If you forgot this theorem and you still wanted to solve this question, you could. Because all you would have to do is figure out what 360 minus 130 is. That's 230. And then plug this into that original relationship where you take half of the big arc minus the little arc. And if you notice, you still get 50 degrees. So either way is fine. All right, I knew this was going to be a long video. I'm sorry, guys. Take care. Bye.